Hey folks, my name's Nathan Johnston. Welcome to lecture 26 of Advanced Linear Algebra. Today is all about something called the Cayley-Hamilton Theorem, and this theorem is the first big consequence that we're going to get from sure triangularization that we learned last class. Okay, and what it is it's a theorem that says, well, if you've got a square complex matrix, and again, the reason we need a complex matrix here is because sure triangularization needed a complex matrix. Okay, so what it says is if you got a square complex matrix with characteristic polynomial equal to whatever it is, so remember the characteristic polynomial, it's the polynomial that you construct to find the eigenvalues of a matrix, so it's this determinant of a minus lambda I. Well, what the theorem says is if you plug the matrix A itself into this polynomial, you're always going to get the zero matrix popping out. Okay, so there are a couple things to clarify before we actually get to the proof of this theorem, okay? So this is a little bit wonky because remember, like this polynomial here, this characteristic polynomial, it takes in numbers and spits out numbers, but here we're feeding in a matrix and expecting a matrix output. So what exactly do we mean by that? Well, we mean sort of just the most naive thing that we could mean. So let's go through a quick example here to clarify exactly what I mean by the Cayley-Hamilton theorem. Okay, so let's just pick some matrix randomly, say 1, 2, 3, 4. Let's construct its characteristic polynomial. Okay, so its characteristic polynomial, you just take A, subtract lambda off the diagonal, take the determinant of that, you're going to get 1 minus lambda times 4 minus lambda minus the product of the off diagonal, so minus 6. And then we unravel that and expand it all out, and we're going to get lambda squared minus 5 lambda minus 2. Okay, so this is P. This is this P up here. This is the characteristic polynomial. Okay, now what the Cayley-Hamilton theorem says is if I plug A into this polynomial, I'm going to get the zero matrix. And what we mean by that is if we replace all of the lambdas by the matrix A and compute the corresponding power of that matrix A, then we're going to get the zero matrix. Okay, so lambda squared is going to become A squared. 5 lambda, that's going to become 5A. And then be a little bit careful here. You can't just subtract off 2, right? Because you can't do matrix plus matrix minus the number 2. Okay, so here, whenever you've got just a scalar by itself, we do that scalar times the identity matrix. And sort of the justification here is think of this as a minus 2 times lambda to the power 0. Think of there as being a little invisible lambda to the power 0 here. Lambda to the power 0 is 1, and similarly, a to the power 0 is the identity matrix. Okay, so you're just replacing lambda, every power of lambda with the corresponding power of a. Okay, and if we compute this junk here, well, what are we going to get? A squared, you just compute it via matrix multiplication. I'm not doing anything fancy. I just multiplied A by itself and got this matrix here, 7, 10, 15, 22. And then minus 5A, well, minus 5A, and then minus 2 times the identity matrix. And if you go through and actually compute this ugly sum and difference and scalar multiples and everything, you're going to find that, yeah, you get exactly the zero matrix, right? For example, in the top left entry, here I've got 7, minus 5, minus 2, oh yeah, that's 0. Okay, and similarly for the other entries. The magic of the Cayley-Hamilton theorem is that this always happens. No matter what square complex matrix you start with, if you plug a matrix into its own characteristic polynomial, you always get the zero matrix popping out on the right-hand side. All right, so let's see where this comes from. Okay, let's prove this theorem here. Okay, and again, because we're working over the complex numbers, we can make use of complex number theoretic specific facts here. Okay, so we're going to make use of the fundamental theorem of algebra, just like we did when proving sure triangularization. It says that we're going to be able to factor the characteristic polynomial as a product of linear terms, right? Because the fundamental theorem of algebra tells us, yeah, you can find a root of this polynomial, and then you factor out that linear term. And then you can find a root of the remaining polynomial, and you can factor out a linear term, and so on, and so on, and so on. So you can keep factoring it until you get it just as a product of linear terms. Okay, so these lambdas with no subscripts, those are the variables in the polynomial. And these lambda 1, lambda 2, down to lambda n's, those are the roots of the polynomial. Those are the eigenvalues of A, in other words, right? The roots of the characteristic polynomial are the eigenvalues of the matrix A. Okay, so what happens if we plug the matrix into that polynomial? Well, now what you're going to get is, well, each power of lambda just gets replaced by A, so you're just going to get all these lambdas becoming A's. Okay, and then remember, scalars just turn into identities, right? Okay, so lambda 1 minus lambda, that's going to be lambda 1 identity minus A. Times lambda 2 minus lambda, well, that's going to be lambda 2 identity minus A, and so on down the line. Okay, so this is the polynomial that we're going to get if we plug A into the characteristic polynomial. Sorry, this is the matrix that we're going to get if we plug A into the characteristic polynomial. So our goal is to show that this matrix here is the zero matrix. All right, so how do we do this? Well, as sort of hinted by the structure of this week's course notes, we're going to sure triangularize A, and that's going to help us here. Okay, so write A as UTU star, which we know from the previous lecture we can always do for a square complex matrix. Okay, so U is unitary, T is upper triangular. And then what we're going to do is we're going to sort of expand out the characteristic polynomial. We're going to expand out P of A using this sure triangularization. So P of A, well, that's going to be P of UTU star because A is UTU star. Okay, and now I'm just going to plug UTU star in everywhere that I see A over on the right-hand side in this equation here. Okay, so I get lambda 1i minus UTU star, lambda 2i minus UTU star, all the way down to lambda ni minus UTU star. Okay, and now the idea is I want to pull those U and U stars out of there. I want to get rid of them as much as I can. Okay, so what I'm going to do is I'm going to notice that, hey, if I pull a U out on the left of this bracket and a U star out on the right of this bracket, then I get this first term here. I get U lambda 1i minus T times U star all on the right, right? When these two terms come in and multiply by the I still get an I, and when they come in and multiply by the T, I get this UTU star. And then I do the same thing on the second factor here, right? I can pull a U and a U star out on the left and right respectively of the second factor, and I get those terms there. And so on down the line. I do that for all of the factors in this big ugly product here. Okay, and the reason I do that is now there's going to be a bunch of U's and U stars that cancel, right? Anywhere that I've got a U star next to a U, well, they're unitary matrices, so they go away. They just turn into an identity matrix, right? So U star U, goes away. There's a U star and there's another U right beside it, beside the third factor in this product here, and those go away all the way down. All of these products of U stars and U's in the middle go away, and I'm just left with a single U left on the left and a single U star left on the right. Okay, and I've just got all the products in the middle here. They're the same as these products, except there are no U's in them. There's just identities and T's now. Okay, and the nice thing about this is this term in the middle here, that's exactly P of T, right? That's what I get if I plug T into this characteristic polynomial. Okay, so I just get U times P of T times U star at the end of the day. So, whereas I originally wanted to show that P of A equals 0, right? Remember, that's my goal, is to show that P of A equals 0. That's what the Cayley-Hamilton theorem says. Well, if I can show that P of T equals 0, that's enough, right? Because then I'll have U times 0 times U star, trace it back, that equals P of A. So if P of T equals 0, so does P of A. So that's my new goal, okay? I want to show that P of T equals 0. Okay, so how do we do this? Well, we're going to make use of the fact that T is upper triangular to simplify the calculation a whole bunch. Okay, so let's sort of write it out sort of explicitly using big ugly matrices. Okay, and the first thing that I'm going to do before I write it out using big ugly matrices is I'm going to make one sort of simplification here. Remember from previous class, whenever you do a sure triangularization of a matrix, the diagonal entries on the matrix T, on the upper triangular matrix, are the eigenvalues of the original matrix. So I know that the diagonal entries of T are lambda 1, lambda 2 up to lambda n, okay? And without loss of generality, I can assume that they are in that order, okay? I'm going to assume that lambda 1's at the top left, lambda 2 is the next one down, and so on down to lambda n, okay? There's no problem doing that, okay? You're free to choose whatever arrangement of the eigenvalues you like in a sure triangularization. You can find a sure triangularization that does it, okay? So, well, if I want to compute this junk, if I want to compute P of T and see that it equals 0, well, that's lambda 1 I minus T and so on down the line. It's all those products. I'm going to write down what these matrices in this product here look like a little bit more explicitly, okay? So I'm going to write down more explicitly like this, okay? So this first matrix in the product, this is lambda 1 I minus T. The second matrix, this is lambda 2 I minus T. This is lambda 3 I minus T. And so on down the line, this last one is going to be lambda Ni minus T. Okay, and now what I'm doing here is I'm writing zeros everywhere that I know there's a 0 in that matrix. And I'm just using stars everywhere I don't know what's happening there, okay? I'm just saying, hey, there's a star here. Okay, that means there's some number there. Maybe it's 0. Maybe it's not. I don't know what's happening there. Okay, and now, so I'm just sort of concerned about the 0 pattern in these matrices. So let's focus on lambda 1 I minus T for a second. In lambda 1 I minus T, well, remember what's happening in T. T is upper triangular. Lambda 1 I, that's just the matrix with lambda 1's down its diagonal, okay? So it still has zeros below its diagonal, right? It's still an upper triangular matrix just because it's diagonal minus upper triangular. Okay, you're not doing anything in the bottom left corner. All right, but there's one more zero there. Okay, there's an extra zero also in the top left corner, and why is that? Well, let's look at the top left corner of this matrix, lambda 1I, is lambda 1. What's the top left entry in T? Also lambda 1, right? I'm assuming, like, we know that these eigenvalues are the diagonal entries of T, and I'm assuming that lambda 1's up at the top left corner. Okay, so lambda 1I minus T, yeah, it's upper triangular, but with this extra zero in the top left corner. Similarly, lambda 2I minus T, it's also upper triangular. Okay, again, it's just diagonal minus the triangular matrix, still going to be upper triangular. Except you get one more zero entry. You get a zero entry this time in the 2, 2 entry. And why is that? Because all the diagonal entries of lambda 2I are lambda 2, and the second diagonal entry of T is lambda 2. So I get a lambda 2 minus lambda 2 in that 2, 2 entry, which is just 0. Similarly, for lambda 3I minus T, I'm going to get a 0 in the third entry, third diagonal entry, and so on down the line. Lambda Ni minus T, now I'm getting a 0 in the nth diagonal entry, in the last diagonal entry, right? I'm going to get lambda n minus lambda n down there, so it's a 0. All of these are upper triangular, just with a 0 in the corresponding diagonal entry as well. So we get one extra 0. And in fact, it's that one extra 0 happening all the way down the diagonals of these matrices that are going to make the product of the entire thing equal 0. All right, so now that we're sort of comfortable with the shape of each of these individual matrices, let's start multiplying them together and see what happens. And I'm going to start off by multiplying together these two leftmost matrices. Okay, so that's my next step. If I multiply together those two leftmost matrices and keep all the others alone, I'm not touching them yet. Okay, so this third matrix, I just copied it down here. Okay, and this last matrix, I just copied it down. I didn't do anything over on the right-hand side here. All I did was compute this product is now going to look like this. All right, and where does this come from? Again, stars just mean I don't care. I don't know what's happening there. But why are there extra zeros this time? Well, let's focus on the leftmost column. Okay, remember the way matrix multiplication works is it's rows of the left matrix dotted with columns of the second matrix. Okay, so it's going to be this row dotted with this. Well, here, I mean, you always get zeros hitting each other when you do this dot product. You're going to get 0 times something and then a whole bunch of something times zeros. Okay, so I'm going to get a 0 in that top left entry. But then the exact same thing happens in the next entry, right? It's going to be this row dotted with that. Again, it's always zeros hitting each other. So I'm going to get a 0 in this entry now. And now if I go down from either of those, well, now it's going to be this row dotted with this and this. Again, all zeros. So I'm going to get zeros in those two entries. If I do this row dotted with this or this, again, it's always zeros multiplying to each other. So I'm going to get zeros in these entries. And the same thing's happening all the way down. Because this first column is all zeros, and because there's only one non-zero thing in these first two columns, I'm always going to get zeros in these first two columns when I do that matrix multiplication. Okay, it's all zeros here, and the only non-zero stuff being tucked up in this first row. It's those two facts that make these first two columns equal 0. And other than that, it's just upper triangular. I don't know much more than that. Okay, it's upper triangular, except the top left 2 by 2 block is all zeros now. So the way to think about this is after I multiplied the first two matrices, I went from having a 0 1 by 1 block at the top left. Now I have a 0 2 by 2 block at the top left. Okay, and I'm going to gloss over some details here, but what's going to happen now is when I do the next multiplication, I'm going to have a 0 3 by 3 block at the top left, right? I've sort of got this 2 by 2 0 block is going to hit this piece here. And then, I mean, this is just hitting that. These first two zeros are always going to hit these first two non-zeros, but then I've got an extra 0 here that makes sure that I still get zeros in that top left 3 by 3 block. Okay, so if you go through the matrix multiplication, after this next multiplication, you'll have a 3 by 3 0 block up there. After the next step, you'll have a 4 by 4 0 block at the top there. After you go through all n steps, you're going to have an n by n 0 block, which is the whole matrix. The entire friggin' thing is going to be zeros after that. And then you're done. Okay, so yeah, the product of all these things, as long as you got a triangular thing here, really is going to be the zero matrix, which is what the Cayley-Hamilton theorem says. Okay, so from that, once you're done that calculation, then you're done. All right, so what sorts of things does the Cayley-Hamilton theorem really tell us? You know, what can you do with it? And really, the point of it is, it tells us that, you know, every single power of a matrix, it lives in sort of a smaller space than it would have if we didn't have a theorem like this, right? The space of n by n matrices, remember that's n squared dimensional. But one way of thinking about the Cayley-Hamilton theorem, it tells us that the nth power of a, well, that's going to be a linear combination of all of the lower powers, right? All of these, and again, that's just because if you write out the characteristic polynomial, you know, it's a degree n polynomial. You add them all up, you get 0. So there's some linear combination, some linear dependence there between those n matrices, between the first n powers of a. Okay, so in other words, the way to look at this is all powers of a, they live within some n-dimensional subspace of the n-squared dimensional space that they actually live in, you know, in some n-dimensional subspace of the n-squared dimensional space Mn of C. Okay, so let's go through a couple examples, see how we can actually make use of this. What sort of computations does this actually make easier? All right, so so the first example that we're going to go through is we're going to find a formula for a to the power 4 as a linear combination of a and I, okay, where a is, you know, it could be any 2 by 2 matrix, but just for the sake of picking some, here's the 2 by 2 matrix that we're going to do. We're going to do 1, 2, minus 2, 1, okay, and we're going to use the Cayley-Hamilton theorem to do this. So first thing that we're going to do, to be able to use the Cayley-Hamilton theorem, we have to know what the characteristic polynomial of the matrix is. So let's just compute that characteristic polynomial. Let's compute determinants of a minus lambda I. Okay, and it's just determinants of that matrix with minus lambdas on the diagonal, and we're just going to get 1 minus lambda times 1 minus lambda, and then careful with your double negative here, it's going to be plus 4 from the backward diagonal term. Expand it all out, you get lambda squared minus 2 lambda plus 5. So the Cayley-Hamilton theorem then tells us that if I plug a's into that, I get the 0 matrix. So Cayley-Hamilton tells me that a squared minus 2a plus 5i equals the 0 matrix. All right, now why is this useful for coming up with formulas for large powers of matrices? Well, because you can rearrange this, right? I've got an a squared equals some other junk here if I just move these two terms over to the right-hand side. Okay, I get a squared equals 2a minus 5i. Okay, I'm going to make use of this equation over and over and over again, so I'm just going to give a name to this equation here. I'm going to call it equation star, okay? I'm just going to give it this little name here so that you know when I'm referring to it. All right, so I know a squared equals 2a minus 5i, and you can do this sort of thing for any matrix. You can always write the nth power of the matrix as a linear combination of lower order powers of that matrix. All right, so what I'm going to do, I actually want a formula for a to the power 4, so I'm going to take this equation here and just multiply it by a and see what I get. Okay, so now I get a formula for a cubed. It's going to be 2a squared minus 5a, so I've just increased the power of a in each of these terms by 1. And now I'm going to say, oh, well, a squared, I've got a formula for a squared, so I'm just going to plug that in. I'm going to replace a squared by 2a minus 5i. I'm going to use star. I'm going to use that equation star. And then just simplify it a little bit, okay? If I expand this out and collect like terms and simplify, I'm just going to get minus a minus 10i, okay? So a cubed equals this linear combination of a and I. And now I can just do that same thing again, okay? I just multiply this equation now by a again, and what I'm going to get is now I'm going to get an equation for a to the power 4. The power is going to go up again. Multiply these by a, so the powers in them go up by 1. And then again, a star, oh cool. Or sorry, a squared, that's just equation star. I can plug that in, that's 2a minus 5i. Plug it in, simplify, I'm going to get minus 12a plus 5i, okay? So that's how you write a to the power 4 as a linear combination of those two matrices, okay? And this is true, like no matter which power of a you want, you can always write it as a linear combination of these two matrices, right? And that's very, very not obvious. That's very unintuitive. Why should every single power of a be some linear combination of these two matrices? Why should every power of a just live in the span of these two matrices? When, I mean, like there's a 4-dimensional space, right? It's M2, it's the 2 by 2 matrices, this 4-dimensional space, but all of the powers of a actually just live in this 2-dimensional subspace of that 4-dimensional space. That's kind of weird, right? So that's what the Cayley-Hamilton theorem tells us. Okay, and I mean, if you just want to sort of explicitly double check this, if you want to see that this formula that we came up with here is right, I mean, just expand it out. Minus 12 times a plus 5 times the identity matrix just equals this junk here. And if you compute a to the power 4 directly, just via matrix multiplication, you'll find that, yeah, that's the right answer. Okay, so we're comfortable with that. Yeah, a to the power 4 really is this linear combination of a and I. Okay. And yeah, you can actually go the other way as well. Rather than just computing large powers of a matrix, you can also compute sort of negative powers. You can go back the other way. So that's what we're going to do in this next example. We're going to take that same matrix, okay, so the same matrix, 1, 2, minus 2, 1, and we're going to find the inverse of it via the Cayley-Hamilton theorem. In other words, we're going to find the minus 1th power of it. Okay, and the way that we do that is, well, we're going to leech off, we already computed the characteristic polynomial, so we're not going to do that again. We're going to leech off of that equation star that we already had, a squared equals 2a minus 5i. Okay, and we're going to rearrange that and we're going to solve for the identity matrix. And if you solve for the identity matrix in this equation here, you will find a formula for the inverse. The way it works is, okay, so 5i equals 2a minus a squared. Now just divide both sides by 5, so you have just the identity matrix on one side. So identity equals this chunk here. And what's always going to happen if the matrix is invertible, you're going to be able to factor out one copy of that matrix here. Okay, so if we do that, if I factor out 1 power of a, I'm going to get a times, well, just whatever's left over, right? So 2/5 times the identity matrix, and then 1/5 minus a, so minus 1/5 a. So that's the junk that's left over. Okay, and the point of doing this is if you have identity equals a times something, you know that something must be the inverse of a, right? If two matrices multiply to the identity matrix, they're inverses of each other. Okay, so this junk here, it must equal a inverse. Okay, so that's our conclusion. A inverse equals this linear combination of a and the identity matrix. And again, if you want to convince yourself of that, if you want to double check this, you can, right? Just plug in identity matrix here, a here, solve it, and you'll see that, yeah, I mean, this really is the inverse of a. You can find the inverse however you like, or multiply this by a and see that you really get the identity matrix, okay? So not only are large powers of a linear combinations of identity matrix and a, but also the inverse of a is a linear combination of a and the identity matrix, and so are things like a to the power minus 75, okay? You can go down as far as you like. All right, so that'll do it for this class. I will see you all soon for lecture 27.